Welcome to a brand new section, networking. This topic is about enabling your Python programs to communicate with other computers, whether that's downloading data from a website, sending an email, or even creating your own custom client-server applications. 1. What is networking? In simple terms, networking is the process of exchanging data between different devices across a network, typically the internet. Every time you open a web page or send a message, you are using networking protocols like HTTP or TCP/IP. Our goal is to make Python the client or the server in these exchanges. 2. High-level networking. URL-lib.request. Python provides several easy-to-use modules for common tasks like downloading files and web pages. The standard library module URL-lib.request is one such high-level tool. It handles all the complex protocol details for you, letting you fetch data with just a few lines of code. We will use this module first to quickly grab content from the web. 3. Low-level networking, socket. For building custom servers, real-time client applications, or simply gaining deep control over the network connection, we turn to the socket module. Sockets provide the foundational mechanism for network communication. Learning sockets lets you define how data is transmitted, giving you the power to create almost any type of network application. Networking in Python involves two main approaches: high-level tools like URL-lib.request for simple web tasks, and low-level tools like Socket for building custom client-server applications. Our next lecture, 27.02, Downloading HTML. See you there. Welcome back. Our first practical exercise in networking is downloading the raw HTML source code of a web page. We will use the built-in URL-lib.request module, which is the standard Python library for opening URLs. 1. Importing and defining the URL. We import the necessary module and define the URL variable. For this example, we will download the HTML of the W3 Schools homepage. 2. Opening the URL. We wrap our network call in a try except block to handle connection errors. We call URL-lib request URL opened parenthesis, which performs the HTTP request and returns a response object. From this object, we can get the HTTP status code. 200 code means the request was successful. If so, we call response.read parenthesis, which downloads the entire content as raw bytes. 3. Decoding the bytes. Since all network data is transmitted as binary bytes, we must convert these HTML_bytes into a readable Python string using the .decode parenthesis method, specifying the UTF-8 encoding, which is standard for web content. Finally, we print the first 500 characters of the string, which will show the raw HTML source code. To summarize, we successfully fetched text data from the internet. Our next lecture, 27.03, Downloading an image. See you there. Welcome back. We successfully downloaded HTML, which is text data that needs decoding. Now, let us tackle binary data by downloading an image file from the internet and saving it to our local system. The key difference lies in how we handle the file content. 1. Defining URL and local file. We define the image underscore URL. I'm using a placeholder URL that serves a random image, but it could be any direct link to a JPG or PNG. We also define the desired output file name, local underscore file name. 2. Downloading the binary content. We use the with statement to open the URL and ensure the connection is automatically closed. We call response.read parenthesis, which returns the image content as raw binary bytes. Since it's binary, we do not call .decode parenthesis, which would corrupt the image data. 3. Saving the bytes to a file. This step is crucial. We open a local file using the file name we defined, but notice the mode, WB. The W stands for write, and the B stands for binary mode. This tells Python not to perform any text encoding and to write the raw bytes directly to the disk. We then call file.write parenthesis, passing the raw image underscore bytes, completing the download and save operation. To summarize, we have seen how to handle both text and binary data using high-level networking tools. Our next lecture 27.04, Socket Programming. See you there. Welcome back. While high-level functions like URLLIB are convenient, they hide the true complexity of networking. To build custom applications like chat systems or file servers, we must use the low-level foundation, socket programming. 1. What is a socket? Think of a socket as the endpoint of a two-way communication link between two programs running on a network. It is what allows the operating system to send and receive data. Every connection you make, from a web browser to an email client, uses sockets under the hood. In Python, we use the socket module to access this fundamental mechanism. 2. Creating a socket object. To create a socket, we need two main parameters. The first is the address family, and we use AF_INET for standard IP version for networking. The second is the socket type. We use sock_stream for TCP, or Transmission Control Protocol, which is connection-oriented and reliable. This combination is the standard for almost all Internet applications like HTTP and FTP. 3. TCP versus UDP. When choosing the socket type, you choose between TCP and UDP. TCP, or sock_stream, is reliable. It ensures data is delivered in order and without errors, making it suitable for file transfers and web browsing. UDP, or sock_DGRAM, is faster but unreliable, suitable for video streaming or gaming, where losing a packet is acceptable for speed. To summarize, we now know the components needed to create a socket. Our next lecture 27.05, Create a Server. See you there. Welcome back. We are now ready to build our first custom network application. To handle incoming connections from clients, we must create a server. A TCP server follows a specific sequence of steps: socket, bind, listen, and accept. 1. Setup and socket creation. We import the socket module. For local testing, we are explicitly setting our host to the local loopback address 127.0.0.1. This ensures the server is only reachable from our own machine. We choose a port number above 1023, as ports below that are reserved. Then we create our TCP socket S. 2. Bind and listen. The server must be bound to a specific network interface, the host, IP, and a port. The s.bind parenthesis method assigns this address to the socket. Next, s.listened parenthesis puts the server into listening mode. The argument 5 is the backlog, which means the maximum number of pending connections the operating system will hold before refusing new clients. 3. Accept connections. The server then enters an infinite loop. The s.accept parenthesis method is blocking. It halts execution until a client connects. Once a client connects, it returns two values: a new socket object, CONN, used only for communicating with that client, and the client's address, ADDR. For simplicity now, we immediately close the connection, but this is where the real data exchange would happen. To summarize, our server is listening. Now we need a program that can initiate a connection to this server. Our next lecture 27.06. Create a client. See you there. Welcome back. We have our server listening patiently. Now we need the other half of the conversation, the client. Creating a client is much simpler than creating a server, as its primary job is just to initiate and maintain the connection. 1. Client setup and connection. The client must know the server's address, so we use the same host and port values. We create the socket S using the standard TCP settings. Crucially, we use the with statement to ensure the socket is automatically closed, even if errors occur. The s.connect parenthesis method initiates the connection handshake with the server, which is the only step required before sending data. 2. Sending and receiving data. All data sent over a socket must be in bytes. We take our string message, hello, server, and use .encode parenthesis to convert it to bytes. We use s.sendAll parenthesis to ensure all bytes are sent. To receive data, we use s.recv parenthesis, specifying the maximum buffer size, usually 1024 or 4096 bytes. The received data, which is in bytes, is converted back to a string using .decode parenthesis. 3. Updating the server for communication. For this client to work, we need to modify the server code we wrote previously. Instead of immediately closing the connection, the server must now receive the data using conn.recv parenthesis. It then processes the data, here converting it to uppercase bytes, and sends the reply using conn.sendall parenthesis. The server's work is finished, and the connection socket, conn, is automatically closed when it exits the with conn end block. To summarize, we have a fully functional TCP client-server model. Our next lecture 27.07. File server. See you there. Welcome back. We are upgrading our simple client-server model to handle the transfer of a large asset, a file. Our goal here is to create a robust file server that can read a file in chunks and send it through the socket connection. 1. Server setup and initialization. We define the host and port as before. We introduce file underscore to underscore send, which is the name of the file we want to transfer, and buffer underscore size, which defines how many bytes we will send at a time. Using a small buffer size is crucial for large transfers, as it prevents memory overload and ensures data is sent reliably over the network. 2. Handling the client connection. Inside our handle client function, after accepting the client connection, we open the file in binary read mode, RB. We then enter a while true loop. In each iteration, we use file.read parenthesis with the buffer underscore size to read a data chunk. When file.read returns an empty chunk, it signifies the end of the file and we break the loop. Crucially, we use conn.sendall parenthesis to transmit the raw binary data underscore chunk to the client. 3. The main server loop. The main server logic remains the same. Create, bind, and listen. The while true loop accepts the incoming connection and then calls our handle client function with the new connection socket. Note: in a production application, you may use a thread here to allow the server to handle multiple clients concurrently, which we learned in the previous section. To summarize, our server is ready to stream the file. Our next lecture 27.08, File Client. See you there. Welcome back. Our file server is ready to stream content. Now we must implement the file client to connect, receive the incoming binary chunks, and correctly stitch them back together into a local file. The core difference here is that the client must continuously receive data until the server closes the connection. 1. Client setup and connection. We match the servers, host, and port. We define the output underscore file name, which is where the received data will be saved. The buffer underscore size must also match or be larger than the server's sending chunk size to ensure we can capture all data efficiently. 2. Receiving and saving the file. After connecting, we open our local file in the critical binary write mode, WB. We enter a while true loop. In each loop, s.recv parenthesis attempts to read up to buffer underscore size bytes. When the server finishes sending the file and closes its connection socket, s.recv parenthesis returns an empty bytes object, which is not bytes underscore received is true, and we break the loop. For every chunk received, we use file.write parenthesis to append the raw binary data to our output file. To summarize, you now know how to build a client-server application that can reliably transfer binary files. This is the foundation of many powerful tools. Our next lecture 27.09, Sending Emails. See you there. Welcome back. In this part of the networking section, we tackle one of the most common automation tasks, sending emails directly from a Python script. We will use two powerful modules from the standard library, SMTPLIB for the network connection and email for message formatting. 1. The SMTP protocol. To send an email, your Python script acts as a client, connecting to a mail server like Gmail or Outlook using the SMTP or Simple Mail Transfer Protocol. This protocol requires you to authenticate with your email credentials and specify the sender, receiver, and message content. 2. Module 1, SMTP/LIB4 connection. This module is the client-side implementation of the SMTP protocol. We create an SMTP/LIB.SMTP object, providing the server address and the port, which is 587 for TLS encryption. Since modern servers require a secure connection, we must call SMTP_server.start TLS, parenthesis to upgrade the connection to TLS, or transport layer security, before authenticating. 3. Module 2, email for formatting. While SMTP/LIB handles the transmission, the email module structures the message correctly using standards like MIME. We import MIME text to create a new message object, MSG. We then use dictionary-like access to set the header fields, like subject, from, and to. These headers are mandatory for a valid email, and email ensures they are formatted correctly for SMTP. Sending emails requires the SMTP protocol. We use SMTP/LIB for the network connection and secure transmission, start TLS, and the email module, e.g., MIME text, to format the message headers and body. Our next lecture 27.10. Generate Gmail app password. See you there. Welcome back. Before we write the final email client, we must address a security measure enforced by modern email providers like Gmail. You typically cannot use your main account password to log in via SMTP anymore. Instead, you need a specialized app password. 1. Why an app password? Gmail requires this step for security, especially if two-factor authentication or 2FA is enabled, which it should be. The app password is a unique, one-time generated password that grants limited access only to the specified application, making it much safer than using your primary login credential. 2. Prerequisites, two-step verification. You must have Gmail's two-step verification turned on to generate an app password. If you do not have it enabled, pause the video and turn it on now. 3. The generation process. Access the following URL: https://myaccount.google.com/app-passwords. You may be required to enter your password and blah blah. Then you see this appearance. You may name the app SMTP client, then click on Create. Then you see a 16-character password, which is your app password. 4. Save the app password. Crucially, copy and save this password immediately. This 16-character string is the password you will use in our Python script in place of your main account password. To send emails via SMTP with Gmail, you must have two-step verification enabled and generate a unique app password, a 16-character string. This password replaces your account password in the Python script. Our next lecture 27.11. Email client. See you there. Welcome back. Having set up the app password, we are ready to write the core logic for our email client. This function will use SMTP/LIB to handle the network session and email to structure the message, completing the SMTP process. 1. Imports and connection details. We import the necessary classes. We define the Gmail SMTP server and the TLS port 587. Note the variables for sender_email and app_password. You must replace these placeholder values with your own Gmail address and the 16-character app password you generated in the previous lecture. 2. The send email function. Our function takes the recipient, subject, and body. First, we format the message using MIME text. Second, we establish the connection using smtplib.smtp and immediately call start TLS parenthesis for security. Third, we authenticate using server.login parenthesis, passing the sender email and the app password. Finally, we use server.send email parenthesis, which takes the sender, recipient, and the message converted to a string using msg.as_string parenthesis. The with block ensures the server connection is closed when done. To summarize, we have consolidated all the email logic into one robust function. Our next lecture 27.12. Run Mail Client. See you there. Welcome to the final lecture of our networking section. We have built our send email function using SMTPLIB and email. Now we will execute it to confirm that our automated mail client successfully connects to the Gmail SMTP server and delivers the message. 1. Review of client code setup. Before running, ensure that you have correctly substituted your actual Gmail address for sender_email and the unique app password you generated for app_password. 2. Defining test parameters. We set up the actual variables to pass to the function. For recipient_email, you may use your own email address to confirm delivery. We set a clear subject and body so that we can easily identify this message when it arrives in the inbox. 3. Running the client. We execute the send email function with our defined test parameters. If the connection, authentication, and sending process are successful, the program should print the confirmation message, email successfully sent to. To summarize, you have learned key networking tasks: web downloading, low-level socket programming for custom client-server communication, and high-level SMTP protocol for email automation. Our next lecture 28.01. Introduction. See you there.